The data set of the week. So the data set of the week is a house pricing data set from Iowa. You can, as usual, click the link, download it from Kaggle. We're just going to use the train.csv. What they call test.csv is actually deployment. They don't give any Y values there, so we're going to ignore that and just take train.csv. And let's take a look. So we're going to load in the data set. We're going to train test split, and let's see what we got. So what we got is 80 columns. The thing we're going to be trying to predicting is the sale price. You can imagine this is like a serious business problem that we're solving. There's big companies like Zillow, who's in, like a big part of the company is to predict housing prices. And now there's whole new industries around this. For example, there's a Canadian company called Properly, where they are basically giving someone an instant offer on their home. You want to sell your home? We use our machine learning to see how much it's worth. Okay, you can have this amount of money today, no open house, blah, blah. So yeah, I used to do a bit of work with them. Very interesting stuff, and a lot of kind of business reasons to want to be able to predict how much a property is worth. And you can imagine having a lot more features than this, but there's a lot of interesting features we can see already. The zoning, the area, and the year, and all kinds of things. Okay, so the big thing about this week is that our target column, the sale price, is numeric, which we call regression. So all up to now, how long has it been? 4.5 weeks of this course. We've only been doing classification. And in fact, we've only been doing binary classification where there were just 2 categories, but you can also have multi-class classification with more than 2 categories. But this week we're predicting a number. And this introduces a whole lot of new interesting issues that we have to think about. And that's what we will be thinking about on today and Thursday. This is our data set of the week. We'll be sticking with it for the whole week and thinking about issues specific to regression. So we have a very small data set, only 1,000 examples in this data set. You could imagine real data sets about this would be a lot bigger. Yeah, you could look at this, but there's a lot of columns, so it's kind of more than you wanted to see, maybe. We could do the pandas profiling, which I should have ran while I was talking because it takes a couple minutes to run. But if you recall from a couple weeks ago, this is just kind of a nice package to, oh, that wasn't so bad. I guess the small data set. To just let us investigate. So what do we have? We have 48 categorical variables, 32 numerical variables. By the way, it's just doing its best to identify that, but it could be wrong. I mean, it's looking at the Python data type, but that isn't always the real data type. So we have 81 features, 1,095 places, a bunch of 6% missing. We can see all these histograms of the ID column. Yeah, we don't really care about that. But you can see all these different things. Here's a categorical one. Here's a numeric one. Lot area. So lot area, the fact that it's showing it like this makes me feel like there's 1 or 2 houses with just enormous. Oh, here you go. Look. So one of them is 200,000, whatever the units are, probably square feet. But most of them are, where's the median? That's not showing the median. That's too bad. Most of them are a lot less, clearly. So yeah, a lot of interesting stuff we can get out of this. And yeah, I'm not going to go through all 80 features, but there's a lot of good stuff here. And there's details, and there's plenty more. This is even the minimal version. Okay, that's that. Get me out of here. Okay, yes, there's also the data description provided with the data set. Oh, but I'm only sharing my Chrome. I'm not sharing my entire screen. Give me a minute here to try to get ourselves out of that situation. Okay, yeah, so there's a data description here, but this data description.text actually has a lot more information. So what it does is it tells us what each feature is and gives us more information. So this is super useful. As a data scientist or a machine learner, you don't necessarily just want to crunch the numbers without thinking about what the data means. And we've talked a little bit about that. But here we get a ton of valuable information about all the different features. And of particular interest are ones like this. So exterior quality. Remember, Python is just going to pick this up as a categorical variable because there are these 5 values here. But we actually know from talking last week or the week before, I guess it was the week before, we talked about ordinal variables. And this is exactly one of those cases where we don't really want to one-hot encode this feature and have a column for excellent, a column for good, a column for average, fair, and poor, because those are not unrelated categories. They're in order. This is kind of the best and this is the worst. And so we should encode these as 0, 1, 2, 3, 4 or 0, 1, 2, 3, 4 in the other order or whatever. So here's where it really pays off to think about what types of data you have rather than just kind of auto detecting everything and moving immediately on without thinking about it at all. Yeah, so there's, basement quality, there's no basement. This one seems to have like an extra, oh no, that's all the same. I think I remember some of them were a bit different. Yeah, so this one is using different encodings like good, average, MN. And so you can imagine if you want to be really meticulous about this, you should really go feature by feature very carefully and decide how do I want to encode this, ordinal, categorical, all that kind of stuff. Because unfortunately, this ordering system is very slightly different than this ordering system because they use different codes. So yeah, it's quite a mess. Where was I? Any questions about this so far? I see a question from before about the midterm. You won't need to write code on the midterm. Pandas profiling counts the index, yeah, as a column. That's right. That was the ID that we saw. Okay, so what I did to preserve my own sanity is I made a few types of features. I made numeric features. So first I separated X and Y. You've seen that before. I made ordinal features regular, which are ordinal features that use that same scale of excellent, good, average, fair, poor. And then I had some other ordinal features, which was to flag that if you were taking this a bit more seriously, you would separately make a different ordinal encoding for those, but I was too lazy, and so I'm just going to treat these as categorical variables, but I'm separating them to say, hey, if we were going to be more careful, we would ordinal encode those separately. And this is kind of the ordinal encoding that pertains to all of these so-called regular ordinal features that I checked, and they all use this exact scheme. So that's my plan here. Oh, I see a question. Yeah, go for it.
Hey, Mike, can you hear me?
Yep.
Okay. So is this like the one-hot encoding like for the ordinal features, or are you doing something else?
The one-hot encoding is going to be for the categorical features. The ordinal encoding, if I go back to here, it's going to make, this is going to be 0, this is going to, it's just going to make a single column for that feature rather than a bunch of columns for that feature. And it's going to map poor to 0, fair to 1, atypical to 2, good to 3, excellent to 4. And then it's just going to treat it as a numerical feature thereafter.
So is that not what one-hot coding does? Because I thought that's kind of what one-hot coding does.
What one-hot encoding does is it makes a new column for each category. So for example, foundation will be one-hot encoding. There'll be a new column for brick and tile, a new column for cinder block, a new column for poured concrete, and you'll have a 1 in that row corresponding to the actual category and 0s elsewhere. So you'll actually get 6 columns made out of this one original foundation column. Whereas here, you started with one column and you're going to keep it one column, but you're going to turn it into numeric by looking at the order.
Got it. Thank you.
No problem. Yeah, in terms of the basic Python types, they both look like strings. Like EX is a string and slab is a string, but we actually want to treat them differently. We want to turn this one into numeric because there's an ordering to these categories where there's no real ordering that I'm aware of to these categories. Is it always good to use all features? I love it. That is a topic of a lecture next week, so stay tuned for next week, and we will have a lecture called Feature Selection to talk about that question. Okay, yeah, we can also make our own features. So, and we'll talk about that next week as well. But I put in this, would price per square foot be a good feature to add in? And that's just sort of a trick question that I put in for you. And maybe this will be more relevant later, but no, we can make our own features like this, frontage divided by area or whatever, but we cannot make our own features that actually use the target value, the price, because that would be cheating. So no, we can't make a new feature out of the thing we're trying to predict. Month sold and year sold. So, I mean, I'm just leaving those in, but in reality, it depends what that means. So if that means like it was sold at this price in this year and in this month, then no, you're not allowed to have access into that information. If you want to predict its sale price and you already know when it's going to be sold, well, you're not going to know when it's going to be sold. Like if I have a house right now that I'm selling and I'm going to predict how much it's going to sell for, I'm not allowed to know exactly when it's going to sell. And so we have to take that out. If those fields mean when is the last time it was sold, that's totally legit because you will have that information in deployment, and so you can leave those in. And so again, just emphasizing, you can't just think of it as a bunch of numbers. You have to really think about the data. And on your homework assignment for this week, I put in a couple of questions in there where I ask you to think about the data. Any questions on that? Okay. Oh yeah, I'm going to make my pipeline now. Just a quick note that there's this make pipeline syntax that I forgot about in scikit-learn, and it's the same thing as making a pipeline with the pipeline keyword constructor, but it's just a little more convenient because you don't have to name each step, and so the code just looks a little nicer, and they just get default names assigned to them. So it's the same thing as pipeline when you put in the names, but just a little cleaner. So, okay, I'm going to do what we talked about maybe 2 weeks ago, which is I'm going to make a separate pipeline for the pre-processing of each type. So for the numeric, I'm going to impute missing values using the median for that column, and then I'm going to use standard scalar. For the ordinal ones, I'm going to impute the missing values based on the most frequent, and then I'm going to use the ordinal encoder, and I pass in those categories right here. And I mean, the code here is a little gross, but basically I'm just repeating this list for each one of the ordinal variables. That's what this multiplication is. But the important part is I'm passing in these categories. And then I'm going to make a pre-processing pipeline for the categorical variables. In this case, I decided to impute the missing values with its own category, a question mark. I didn't really think this through too much. I just did something. And I'm going to one-hot encode with this ignore. Regarding this sparse equals false, the reason why I was doing that, you don't really need that in the code. It just, when I print things out, I can print things out better for you if I do that. But then I just I realized when I was making homework 5 that I don't actually need this. So I don't learn my lessons, do I? I'm going to take it out and then I'm going to regret this. But I don't learn. Okay, I'm pretty sure we don't need it. Yeah, so we'll just use simple imputer again. I haven't really thought it through too carefully. I may have wanted to get rid of some columns if it was like almost all missing and just not useful. We could check for outliers. We'll talk about that later in the course. And just also note that make pipeline, it's just giving a name. So the simple imputer step is called simple imputer in lowercase, the ordinal encoder step. just because sometimes you need to know the names of the steps in the pipeline for like randomized search CV or something. I'm just pointing out the names. EDA is exploratory data analysis. Okay, yeah, so now I'm going to build the column transformer. You've seen this before. Numeric preprocessing pipeline goes into these features. Ordinal pipeline goes in these features. Categorical pipeline goes in these features. Right. And then, yeah, you may have noticed on Piazza, I accidentally deleted a question in the previous homework that you've already turned in. But this was basically what it was. It was just asking you to print out the transformed columns. And if I'm lucky, awesome. Okay, so here's the transform training set, just so we can see what it looks like. So look at all these nice scaled numeric variables without giant, big, or tiny values. Just all kind of around 0 and 1. Looks great. Look at these nice one-hot encoded variables. I'm loving it. Got some zeros and ones here. And the ordinal variables are stuck somewhere in the dot, dot, dot. I'd actually kind of love to see the, no, what just happened? Uh-oh. Get me out of here, please. Let's see. Ooh. Okay. Oh. Okay. I was going to say I would have loved to see the ordinal variables in between and to see them have like 1, 2, 3, 4, 5. Let me try to show you one of them. Ugh. Show me all of them. Okay, I don't even know anymore. Never mind. There we go. Okay, this is what I wanted to show you. I remember now. Okay, all good. I'm going to find one these ordinal features like exterior quality. That's what I was looking for. And I thought they were going to get renamed, but they're not going to get renamed. There you go. Okay, that's what I wanted to show you. So this exterior quality got mapped like 0, 1, 2, 3, 4, 5 based on, you know, fair, good, all that kind of stuff. So that's what I wanted to show you there. That's the ordinal encoding. So one-hot encoding, you're going to see zeros and ones. Ordinal encoding, you're going to see small integers. And scaled numerical variables, you're going to see stuff like this. That's what I wanted to show. Okay. And then we have, so we had 79 columns before. Now we have 292 columns. That's because of the one-hot encoding, which expanded a bunch of the columns based on the number of categories. And I'm going to run dummy regressor. And well, let me not even show you this yet. Dummy regressor, nice to meet you. You haven't seen this before because we've only had dummy classifier until now. But now we're doing regression. When we do regression, we need dummy regressor. And I'm going to get the score here. And what you see is that the training score is 0 and the test score is negative. And we've never seen a negative score before because we've always been doing classification where the scores were things like accuracy or precision between 0 and 1. But with regression, we cannot really use the same types of scores because the truth is a number and we're predicting a number. And so that's the next thing we're going to talk about is regression score functions. But first, any questions? When we're using ordinal encoding and normalizing the other numeric features, do we need to scale? Awesome question. Yeah, do we need to scale the ordinal features after ordinal encoding them? Yeah, I mean, if it went up to like 1,000, then I guess that'd probably be a good idea. But in this case, I knew it was just from 0 to 5. And so I didn't think it was really a big deal. Even 10 wouldn't really be a big deal. And so it'd just be a bit of extra hassle. But that's an awesome question. And so now I'm going to see, I told you at the beginning that I never learn because, of course it took 20 minutes. Who was I kidding? Human nature, we don't learn. Okay, next section, regression score functions, mean squared error and R squared. So yeah, we're not doing classification anymore. So when we make predictions, well, the predictions are just numbers. And what dummy regressor is doing, remember, dummy classifier looked at the most common Y value and just always predicted that. Dummy regressor looks at the mean, the average Y value, and just always predicts that. And with classification, like when you yourself implemented dummy classifier, and actually I could have had you implement dummy regressor, but I'm not going to. With dummy classifier, you just want to know, was it right or was it wrong? And you can use the equals, the comparison. But here, it doesn't make sense to say, is this number exactly equal to the true number? Because that's always going to be false. It doesn't make sense to just say, is my prediction exactly right? With regression, we want to know how close our prediction was to the true value. And so we need new scoring metrics. Accuracy just doesn't make sense anymore. We want to know for each of these numbers, how close was our prediction? For this true number, how close was our prediction? And so a common one is mean squared error. So I'm going to make my predictions here. I take the truth, I take the predictions, I take the difference between them, that's the error, I square them, I take the mean. And so my mean squared error is whatever, this humongous number, and we'll talk more about that later today. And this is also implemented in scikit-learn. I imported it at the top, so you can look at the import at the top, but I'm just showing you I get the same number. So this is scikit-learn mean squared error. And perfect prediction would have a mean squared error of 0. So if I pretend my predictions are the real answers, then I'll have a mean squared error of 0. And the question is 0 good? And is 6 whatever billion thing this is that good? And the problem is, it kind of depends on the scale of the targets. If we had the targets in dollars, we would get some error. If we had the targets in cents, we would get a different error, or in US dollars or Canadian dollars or whatever. And that's kind of annoying. We never had to deal with units of the targets in classification. They were just categories, but now we have units. And so we have to think about that. And so it'd be kind of nice to have an error metric that didn't depend on the units of the targets. So here's just an example saying if they were in cents instead of dollars, then you'll get a bigger mean squared error, 100 times bigger. And so a popular score is the R squared, and it's kind of like a normalized mean squared error. You can read more about the exact formula if you're interested. I'm not going to go into it, but it's similar to mean squared error. It's flipped. So in scikit-learn, the scores higher is better by default, as you've been seeing so far when you call .score, higher is better. So it's not mean squared error, it's flipped. Higher R squared is better. And the best R squared you can have is 1, just like with classification, the best score you could have is 1. So 1 is perfect predictions. So if you just predict the average like dummy regressor, you get 0. And it is possible for R squared to be negative, but it's not going to happen that much to you in real life. Just in like silly cases with dummy regressor on the test set. So scikit-learn has this R squared. Here, we got 0 from dummy regressor and 1 from putting in the true values. And if you call .score, it uses the R squared by default. So earlier when we had that cross-val score and it was saying 0, because remember cross-val score in scikit-learn calls the .score method of whatever, I can't say classifier anymore because these are regressors, so let me say estimator. It calls .score on your estimator or your model, people often say as well. And so that's why we got those things in cross-val score. Just a very quick note that for mean squared error, it doesn't matter if you switch the order of these two, but for R squared, it does matter. But actually, we've seen things where it does matter even before, like some of those precision recall F1 ROC things. It mattered as well. I just didn't talk about. But in scikit-learn, the convention is always put in the true thing and then the predictions. So just stick to that. And when you call fit, it, roughly speaking, tries to make the score as high as possible. And as we saw with classification, that isn't always what you want. That we saw that maybe your fit makes accuracy good, but you actually care about precision or F1 or one of those other things. And so we'll talk a bit more about that today. And is R squared actually what we want? But first, questions. How about using chi-squared? I don't know. I mean, I know about the statistical test and quantity, but I don't know if that's really used here. What is the negative score for dummy regressive score? Yeah, okay, so let me scroll back up to here. So the formula for R squared, the definition of R squared happens to be such that the best you could get is 1. It's 1 if you're right, if you're exactly right every time. And furthermore, just based on the definition of R squared, if you predict the mean every single time, your R squared score will be exactly 0. And because dummy regressor predicts exactly the mean every time, its score is 0. However, on the training set. However, in terms of cross-validation, it's predicting the mean of the training split because that's what you call dot fit on. It's using those predictions on the validation split. And so as far as the validation split is concerned, your predictions are not actually the mean of those values. They're just very, very slightly off of that. And so you get these very tiny negative values, but they're still pretty close to 0. So that the reason why that's not 0, it's just because the mean of the training split targets is not the same as the mean of the validation split targets. In reality, for any sort of reasonable estimator, you're going to be getting things between 0 and 1. Okie dokie. Any other questions? Comments, concerns, grievances, memes? Okay. Yeah, memes are perfectly fine, especially on Piazza. I even made a memes tag on Piazza if you want to use that. That was kind of fast. Okay. Let me try to say the punchline of what we just talked about. We need a score for regression. And with regression, the things we're trying to predict are numbers. And our predictions are also going to be, this is dollars for the property. This sold for this much, this sold for this much. And our predictions are also going to be numbers. We need a score saying how good our predictions are. If this is 157,000 and we predict 150,000, how good is that? If we predict 200,000, how good is that? And so I talked about 2 different scores. One is mean squared error, and one is R squared. And the real punchline for now is that R squared is the one that is the default in scikit-learn. When you just call dot score, that's what it's going to do by default. And the kind of key takeaways for R squared is that it's going to be 1 if all your predictions are perfect, if every single prediction is exactly equal to the truth. So 1 is the highest value R squared could take, and roughly speaking, 0 is the lowest value. And so it's kind of like the dot score we had for classification before, in that it was between 0 and 1, and closer to 1 was better. And that's, I mean, the details I'm not too worried about right now, but it's basically measuring how close is each prediction to each true value. Yeah, so why are they negative? Yeah, I wouldn't worry about the negative thing. It's a quirk of the definition of R squared, and if you just make extremely bad predictions, you can actually get something that's negative. That is even worse than 0, but in most of our lives, we're going to be living in between 0 and 1. And it's just that the way that R squared is defined, it happens to be possible to be negative if you have horrible predictions, but it's not really particularly special. You can just think of it as a little bit worse than 0, and both are pretty bad because dummy classifier and dummy regressor are in general pretty bad. So it's not the closer a model predicts to the mean, the better score. It's that the closer the model predicts to the true values, the better the score. And if it happens to predict exactly the mean, then the score is going to be 0. Yeah, so that's right. A squared number cannot be negative. I mean, we can, yeah, maybe I should have just written down the mathematical definition of R squared, and that would have been better than avoiding it. But okay, I'm going to call it here and move on. But message received that I might need to beef up this part a little bit. Okay, I want to talk about linear regression for a few minutes, and then we're going to take a break. So linear regression is super popular. We've seen logistic regression before, and they're very similar to each other. In fact, linear regression is just a little bit simpler than logistic regression. With logistic regression, we made predictions. We had these coefficients, one per feature. We multiplied the coefficient by the feature, added that up for all the features, and then we got some number, and then we did something to it to get it into a probability. Linear regression is basically that without the last step. You don't do something to it at the end. So linear regression's prediction is just coefficient times feature plus coefficient times feature plus coefficient times feature. And so they're very similar to each other. There's a lot more on this in other courses. I think Stat 306 may be actually mostly about linear regression for an entire course. And so in scikit-learn, there is something called linear regression. And I'm basically going to suggest as your guide through this topic to not use it and to instead use something called ridge. And so for our purposes in this course, when I say use linear regression, by default, I will mean use ridge. And we're just not going to use the thing called literally linear regression. And I want to show you why. So I'm going to make a pipeline that has our pre-processing from before that we talked about with all that scaling and one-hot encoding and everything. And then I'm going to put a linear regression on top of it. And I'm going to fit it on the training set. And I'm going to make some predictions. Okay, that looks fine. And I'm going to look at the biggest prediction. Ugh. Why is that happening? That is strange. Okay, let's take our break and I'll see if I can figure out what happened there because I remember doing that and it was all good. And I'll see if I can figure it out during the break. So let's break now for 5 minutes. 11:44, the minute just changed. We'll resume at 11:44 and then we'll go into this next section. Hey there, this is CPSC 330 lecture 10, the second half, done again because the Zoom recording disappeared into the Zoomiverse. So where were we? Let me clear the outputs before we start. Oops. And we were at linear regression. And so the class is about regression. We've seen logistic regression before for classification, and linear regression is one for regression. We're going to talk about it more next class. And we're not really going to go into depth. But in scikit-learn, there's something called literally linear regression, and I'm basically going to tell you don't use that. Instead, use ridge, which is similar but less dangerous. And to show what I mean by dangerous, I'm going to make one of these linear regressions. I'm going to fit it on our training set. And yeah, some silly stuff happened in the actual class yesterday with this one-hot encoding. We'll just breeze past that. And so what I'm going to do is I'm going to make predictions on the test set, and these predictions look a little surprising. 10 to the 5, 10 to the 14. So the training set house prices go from 750,000 to 35,000. But the predictions on the test set are some hilarious number, trillions of dollars and negative trillions of dollars. So this model just broke horribly. And we're not really going to go into the details of why that happened in this course. There are other courses that go into that. It's a numerical issue. It has to do with the coefficients, which themselves got messed up. And we're just going to use ridge, and then everything will be fine, and we're not going to go into why this happens. So we use ridge instead. Then the predictions look fine, reasonable numbers of dollars, and they're between $30,000 on the test set and $500,000 on the test set, and so that sounds much better. So that's what we're going to do in this course. If you know more about linear regression and you want to use linear regression in its basic form, you probably want to get out of scikit-learn anyway. So there's the stats models in Python, or you can use R. But I don't think there's a lot of use cases where you really want to be using this scikit-learn linear regression. Okay, so I have made this function here that calls cross-validate, but also takes this, not just the mean of the folds, but also the standard deviation of the folds, and I'm going to try to get us into the habit of using this function a lot. I've provided this to you in the homework as well. And so I'm going to call this function. LR is the variable I named my pipeline with ridge in it. And I get 75% R squared and a pretty huge standard deviation, which appears to be because on this fold somehow it just did terribly, and I plan to investigate this at some point because I'm just so surprised it would do so much worse on one fold than all the others, but haven't investigated that yet. So that's the introduction to linear regression. Next we have exploring alpha, and alpha is the hyperparameter of ridge. A couple things about it. It's positive. When you set it to 0, you're basically going back to linear regression, which I said not to use. So set it to something positive, not 0. And it's basically the same hyperparameter as C in logistic regression, but annoyingly, I'm sure it was done with good reason in scikit-learn, but alpha is the backwards of C. It's kind of like 1 over C. And so large C meant more complex model, better on the training score, and smaller alpha means more complex model, better on the training score. So just something to keep in mind. I skipped this part yesterday, and I think I'll skip it again now. It's not super relevant. It's showing the effect that alpha has on the coefficients, but we don't need to go into that right now. So let's try tuning alpha. So this is our good old loop over different values of hyperparameter. This is basically the same thing as grid search CV, but implemented it ourselves. We've seen plots like this many times. And now, usually when we looked at these plots with the hyperparameter, moving to the right meant more complex model, but alpha is backwards, as we just talked about. So here, moving to the left means more complex model, which is why the training score moves up as you move to the left, and the test score, the cross-validation score, goes up. Here we're kind of underfitting, so it's totally worth it to get more complex. Here we're kind of in the sweet spot, and then here we start overfitting, and the cross-validation score actually gets worse. So the best alpha according to this is 100, which is kind of around here at the peak, 10 to the 2. Just a quick note that scikit-learn also offers a ridge CV, which is just like a convenience that is basically a ridge plus a grid search CV over alpha rolled into one thing, and you just give it some alphas, and when you call fit, it even tunes alpha for you. So it's just a convenience thing. In this case, it picked this alpha, which I think these two look pretty much equally good according to the plot, but maybe it's just doing the cross-validation differently. Okay, that's that. Now back to error metrics. So we talked a bit about error metrics in the first half. We talked about mean squared error, R squared. And so let's go with our linear regression model with alpha equals 100. We can get a training score of 86.86. That's an R squared. We can also get a mean squared error. Just on this screen recording, I'm a bit zoomed out, and so I guess you're seeing more than. Let me zoom in a bit. Okay, this is how it would actually be in class. So let me do this. So this mean squared error is some number that's like a billion, and it can't really be $1 billion. That can't be the error. And the reason for this is that, unlike with classification that we were doing up until now in the course, with regression, our target, our output, our y has units of dollars. And what that means is that our error also potentially has units. The R squared score actually doesn't. It's just between 0 and 1. It's normalized. But mean squared error, because of squared, it's kind of in the units of dollars squared, which doesn't really mean anything to a human. And so I prefer the root mean squared error. And here I'm literally just taking the square root of the mean squared error. And now it's in units of dollars again, and more human readable in my opinion. So we can say the root mean squared error is $30,000. Okay, we're kind of off by $30,000 typically, we could say, and that's something. So we can also make a scatter plot. This is something we couldn't do with classification, but now that our target is a number, this is very cool. So we can put the true price. This is done on the training set in this case, but you could do it on the test set. We have the true price, the predicted price, and for each point, so that this place was actually worth 300 something, we predicted 300 something else, we put a point down. And this black line is like perfect prediction. If you're on the black line, that means your prediction is exactly equal to the true price. And so you got it exactly right. And so with this plot, we can immediately see kind of like how the confusion matrix in classification gave us a bigger picture of what is actually going wrong here. What type of errors do we have here? False positive, false negative. This is kind of like this continuous analog of that. What's actually going wrong here? Well, it was 700, but we said 450. It was 150, but we said 550. And so everything below this line is where the true price was bigger than the predicted price, and so we're under predicting. Everything above the line, we're over predicting. The prediction's too high compared to the truth. So this is a really useful diagnostic for regression. And we'll see more about this tomorrow. So yeah, there's a few cases where our predictions are way off. We do have a lecture on outliers coming later in the course. We'll leave that for now. And here's a question. So we said our root mean squared error was $30,000. Well, are we happy with that? Is $30,000 good? And the answer is it depends. For a house worth 600K, sure, that's 5% error. I can live with that. For a house worth 60K, you don't really want to be off by 30K when you're predicting the price. And so this brings us to thinking that maybe this idea of absolute error, of literally prediction minus true, is maybe not as useful as a relative error or a fractional error, whatever you want to call it, that's a percent of the true price. And so here's the actual values of the true prices in the training set. So they do range quite a lot. You can see here those outliers we saw before. So we can compute percent error. We can get our predictions, and we can say predicted value minus true value divided by true value. That's fractional error times 100 to make it a percent. And what you can see is we have signs here. So we have negative 11 means I was too low. Positive 4 means my prediction was too high. So these are, but this is 11% too low, 4% too high. So these are now in percents, which is nice. And if we want to collapse that, so this is for each example, for each property. But if we want to collapse this into a single number to say how well we did, then before we average these, we should take the absolute value. So the positives and negatives don't cancel each other out. So we take the absolute value, now we get the same thing before, but this just says now off by 11%, off by 4%. It doesn't say too high or too low, because we're basically saying we're fine either way, or we don't have a preference in this case between being too high or too low. More on that tomorrow as well. And so we can have this mean absolute percent error, or MAPE. So this is what we had before, basically percent error with this 100. Then we take the absolute value, then we take the mean. And so here we can see our mean absolute percent error on the training set is 10%. And that's a really meaningful number. I think that's the most human readable error metric we've come up with so far. Saying r squared is 0.8, okay, it's kind of hard to interpret. I mean, it's closer to 1, and 1 is good, and that does tell me something, but it's not that easy to digest. The mean squared error was particularly unhelpful, I thought. The root mean squared error was kind of useful, $30,000, but to me, this is the best number to summarize how well we're doing on the training set for this problem. Although it's a human decision. And so here's our test error. Note that this is an error, so lower is better. It's not a score where higher is better. The fact that test is a bit better than train is just luck, and we have a small data set, so there's going to be a lot of noise here. Next. So if we've decided we care about this MAPE thing, then we could, when we're doing hyperparameter optimization like randomized search CV, we could tell it, hey, optimize this MAPE thing, and that's fine. Scikit-learn allows that, just like scikit-learn allowed you to optimize F1 score or something like that with grid search CV. But with fit, I mean, fit doesn't, so there's two kind of rounds of tuning here. There's the hyperparameter optimization, which is like the outer loop, but there's the actual fitting, which is the inner loop, and no one told fit that we care about this other scoring metric. We only told the hyperparameter optimization. And so that, maybe we can do something about that. And having gone through this yesterday, I thought it was very boring. So let me not go through it in so much detail and just say, here's a fake data set with only 2 houses in it, one worth 50K and one worth 500K, and 2 possible models, maybe linear regression with 2 hyperparameters, maybe linear regression versus random forest. And what I'm showing is that one model, if you look at root mean squared error, the first model looks better, and if you look at MAPE, the second model looks better. And so all that is to say, what the best model is depends on what scoring metric you use. And we did kind of already see that last time with classification. So that, but that's true for fit as well. So if we could tell fit what scoring we're using, maybe it could come up with a better model as well, doing whatever the thing it does. And so without really getting into any detail, I'm just going to throw out a hand-wavy rule of thumb that I'm not even sure how widespread it is, but I believe in it, which is that if you take the log of the y values before passing them into fit, that will tend to get you a better MAPE. And I'm not really going to go into the math here because I tried doing that a bit last year and I just got all muddled. I'm going to throw out this rule of thumb and I'm going to back it up empirically rather than theoretically. Okay, so here's this histogram we saw before. This is our Y train. These are our house prices on our training set. And they go from, what is that, $30,000 to 700 something thousand. If we take the log, then not only do the numbers here change, but the shape kind of changes. And so here, this 5 is basically $100,000 because I took the log 10. So this is 10 to the 5. 6 would be $1 million. And there's a bunch of reasons why you might want to do this transformation. So you might have taken a statistics class where it talks about things looking kind of Gaussian and noise, and this looks a bit more Gaussian and stuff. We're not going to go into that here. There's the fact that the predictions will not be negative if we do it this way, which I can talk about in a minute. And then there's this kind of hand wavy thing I'm just throwing out there saying if you care about percent error rather than absolute error, this can often help. Especially in the cases where you have these big values, because these few big values will kind of dominate the way fit works. But when we take the log, these extreme values don't become as extreme. I guess that's one way you can think about it. Okay, so here's what I'm going to do without saying more than that. I'm going to have my same linear regression model, and now I'm going to fit on log of y train. Notice I'm not using log of base 10 here. It really doesn't matter which base you use, so it's just typical to use the regular natural log. I just did the log base 10 up here for visualization purposes, but we typically just use that regular natural log. And so now when I predict, look at my predictions. This is not $11, $12. This is, I predict the log of the price is 11.8. I predict the log of the price is 12.4. Because if it was trained to predict the log of the price, that's the only world it knows. It just knows, hey, you gave me some x's and some y's, you called fit. I'm going to learn to predict whatever thing you gave me, which is the log of the price. So these are predictions of the log of the price, and we need to unlog them to get actual predictions. And the inverse of log is x. And so we can call predict and unlog them. And now we have actual predictions again: $134,000, $112,000, etc. And what I'm going to do now is show you the MAPE from before. So this is our old model. This is the 10% error we saw before. And then I'm going to call the MAPE on the new thing, which is the model trained on log, and then getting the predictions back out. What you can see is we got about 1% better. And I mean, this is a little, first of all, this is training error. We should be a bit more careful, do cross-validation. We should use lots of folds because this is a small data set. Oh, I actually did that. How nice. So when you're calling cross-validation with like F1 score, with classification, we did things like F1. That's because F1 is like a known type of score in scikit-learn, and so if you just put in the string F1, it knows what you're talking about, but it doesn't know about MAPE, and so you have to do this make scorer thing and pass in my own MAPE function that I wrote, and then you can just pass in whatever score you want. So that's what that's all about. Yeah, okay, so now, okay, so this BAM should go up here. This should go down here. And what I want is really to show, I see, what a hassle. Yeah. Okay. Never mind. I can't exactly call cross-val score on this thing right now because of the prediction, so I still need to deal with that. But I'll be able to do that in a minute. So let's hold off on that for a minute, actually. Okay. So what do you think happened to the r squared, which is just the default score? So the default score in scikit-learn is the r squared. So our r squared before was 0.86, and with this log thing, it was 0.85. And so this is very typical. When we mess around with things, so if you leave things alone, if you just call fit, it'll usually do a good job of the scoring metric that is dot score. If you mess around with it in some way to make it better at some other metric you care about, it'll probably be worse at the original metric. And we actually saw that with classification as well. For example, we messed around with it by setting class weight. That gave us maybe a better F1 score, which we're happy about, but it gave us a worse accuracy because accuracy is the default dot score. So it's very analogous in that sense. Okay, yeah, so about this positive thing, because your prediction is x of something and x of something can never be negative, when you do it this way, your predictions can never be negative, which is a nice bonus, because with linear regression, you might actually predict a negative house price on the test set, which is a bit silly. So that's nice. Another quick note that if you have a house price that's 0 in the training set, it'll throw an error because it'll try to take the log of 0 and pass that into fit. And so it's pretty common to actually do log of 1 plus y instead of log of y, just to not take the log of 0. And NumPy actually has a function log 1p, log of 1 plus the thing, and it's inverse exp of the thing minus 1. And so you can, it's pretty common to just use these instead of log and exp, just to avoid that possible issue. The next thing is just a piece of scikit-learn syntax. It's not really a concept, but just a scikit-learn syntax that scikit-learn provides a more convenient way of keeping track of all this, which is transform target regressor, which basically wraps a regressor. And so you make a transform target regressor, you give it the base regressor, and you tell it, here's how I'm going to transform, here's how I'm going to untransform. And then, and then when you call fit, it automatically applies the transformation for you, and when you call predict, it automatically applies the exping for you. So it's just a bit more convenient. Yeah, and I'm just showing you get the exact same predictions if you expit yourself, or if you use this, and you get the same MAPE if you expit yourself and if you do this. So now I should be able to do, oops, that is completely not what I was looking for. Bam. Okay, so let me see if I can do this. Ha! Okay, so with this transform target regressor, I can now pass it into cross-eval score or cross-validate, because it takes care of the transforming, and so dot predict actually works properly. And since this calls dot score and this calls dot predict, it's all good. So that's actually a nice motivation to use transform target regressor, which I hadn't really thought about before. So that makes a lot of sense. And then I can pass in my own score. And so now I actually have a cross-validation score, and I can even do, I think, well, I can at least do a lot more folds. Yeah, so now I can compare the score of, the MAPE score of the original thing to the log transform thing finally. And voila, the cross-validation MAPE was 11% without log transforming, and now it's a bit lower with log transforming, and I'm already doing a lot of folds of cross-validation, so we can start to feel a bit more comfortable with that. With transform. Okay, that's actually satisfying. These are some choose false questions I posted on Piazza, so I guess we're good to go. This is it. Thanks for watching.